All right. Hello, everyone. You have completed your Doing Paleoanthropology Collaboratively um, team assignment. And this was an exercise in getting you to apply some of the concepts from the Gregory article, Evolutionist Fact Theory and Path, and generally just to kind of set you up for thinking about how we go about doing science. When you're going about designing a project, you can't just like have an idea and then go out to the field and just start doing stuff. You have to come up with a plan. You have to figure out what it is that you know up front. And then from the facts that you have, and of course, if you're doing a legitimate large scale scientific project, you're going to go read literature from other scholars working on similar questions or at the same site or the same species or whatever it is that you're studying. You're going to read that literature. You're going to compile all the facts that you have, also compile the ideas from other people. So you've got as much information as you can before you're going out to the field to do that work. Then you're going to make inferences. So based on the facts that I have, when I put them together, what are some initial conclusions that I can draw? And then finally, from there, you're going to ask the questions that will get you to the kind of additional answers that you need. So what else do I need to know about this thing that I'm studying in order to draw additional conclusions? And that third question, what else do I need to know, is really where the science happens. You figure out your methods for how you're going to go about collecting data to answer those questions. If you're doing hypothesis testing, you might generate some hypotheses. And then you're going to essentially go and do those methods and figure out what it is exactly that you need to do to answer the questions that you have. And so what I want to do is share my screen really quickly and talk through these footprints. And so I want you to keep in mind that when we're talking about facts, we are talking about empirical observations. What can we simply observe by looking at the thing that we're looking at? So I'm going to zoom in really quickly. And so as it currently stands, we've got these footprints. And so facts, as Stephen Jay Gould in the Gregory article says, facts are something confirmed to such a degree that it would be perverse to withhold assent. And that basically means that facts are something that we accept as being true because they've been confirmed to be so. These can be simple observations like, it is a fact that I'm holding a coffee cup. There's coffee in it, and I'm holding this coffee cup right now. You can simply observe that to be true. And there are many things that you can observe about this site. One thing you can observe is that they're footprints, because it tells you that they're footprints right here. So that is a fact. You can also kind of tell that they're footprints. You can see that the footprints are moving from the south to the north. You can know the size of the footprints because we have a nice scale here. You can know the relationship of each footprint to its partner. You can understand the relationship between each footprint to the corresponding footprint. You can know all of the relationships between all the footprints together. You can know that these are, there's at least two individuals here, right? You have these smaller footprints here. You have these larger footprints here. So we can know their direction. We can know the minimum number of individuals. We can know the scale. We can know that they're footprints. We can know that they are not running, right? We can look, we have this photogrammetric scan, and we can see based on the impression that these are individuals that are not running. These are conclusions that we can draw just through simple observations of these footprints. Now, what inferences can we make? Well, based on the relationship of the footprints, we can infer that they are walking next to one another. Why? Because for every small footprint, there's a corresponding large footprint, right? This is a left foot, right foot, left foot. So that's an inference we can make. So we can't know that they're walking. It could be, I mean, it's possible that this individual walked this way and then 25 minutes later, this individual walked this way. But it's very unlikely that that's the case given the relationship of these footprints to one another. We can infer that there are more than 2 individuals here. I think that's something we can infer that's leaning towards we can know. So these are small footprints, right? These are corresponding to one another. They're walking in that direction. But if you look at these large footprints, I'm going to zoom in really quickly. Let me move my drawing tools out of the way so I can click. Oh, of course, I rotated it. We can click and start here. So let's just look at this, for instance. One trick, by the way, if you didn't notice, is that these numbers correspond to the, these are the designations for each feature. So this is footprint, this is individual G1, footprint number 36. If you look down here, though, this is individual number G2 and individual number G3, footprint 27. So these are 2 individuals walking. We can see a heel print here. The ball of the foot is here. Here's the arch of the foot, and here's a big toe. This footprint that I just outlined for you is on top of another footprint. It's a little bit hard to see the additional big toe here, but there's another footprint that basically is right here. It's just been destroyed partially by this footprint. Additionally, big toe, arch, heel, which means, by the way, we can measure about the size of the feet for this individual as well. And then we have it's stepping on top of another big toe, which is, I believe, right here. And then, of course, the rest of the footprint is destroyed. So something else that's happening here is you have an individual walking in the footprints of another individual. So that's an inference we can make. We can infer that all 3 of these individuals are walking together because of that relationship, right? That there's, there's one individual walking behind the other one. Now, who is walking next to whom? I don't know. And that might not be a conclusion that we can draw. Finally, the third question is, what other things do we need to know? So we need to know the matrix. So what are these footprints in? We need to know, that can tell us potential dating methods. That can tell us how they were preserved. It's hard to draw with a mouse. Preserved. And we need to know, of course, the location. The dating plus the location can tell us who left these footprints, what species left these footprints. And so we'll start with the location. This is in Eastern Africa at a site called Laetoli. Laetoli, spelled this way. You're more than welcome to look. So these are real scans of real fossil footprints, by the way. So you're more than welcome to look these up. What's the matrix? The matrix is like, what's the fossil depression in? So what do we find that in? And it's a mixture of mud and volcanic ash. And so what that tells us is that there's a volcanic eruption. Now we can go, okay, where would an eruption be happening? Of course, it's pretty far that way. So this is a group of individuals walking away from a volcanic eruption. They're not running away from it, by the way, because they're not like right next to the volcano. They're simply moving away from that area. And there's actually not just these footprints. There are loads of footprints from all different kinds of animals moving away. So the matrix is mud and volcanic ash, and that's really good because we can do several different dating methods here. We can do potassium argon dating. We can't do carbon dating, by the way, because volcanic ash doesn't have carbon. And there's 2 reasons we can't do carbon dating. One, there has to be carbon in the source in order to do carbon dating. The second reason is carbon dating is only good to somewhere between 50 and 70,000 years into the past, and only for terrestrial beings. So it doesn't work very well for ocean beings because the carbon isotope that we use to look at the radioactive decay of carbon, is incorporated into the body of organisms in the water at variable rates. But for terrestrial animals, animals that live on the land, and for plants, it happens at a regular rate. And so we can't use carbon dating because there's no carbon here to date, and this site is much too old. So it's not a good tool for the job. So we want to make sure we use the right tool for the job. But we can still do radiometric dating. We're just not carbon dating. We can do potassium argon dating. This is the decay of a potassium isotope into an argon isotope. We can do, not that. We can do, let's see, we can do potassium argon dating. We can do argon dating. So we can look at the decay of one argon isotope into the decay of another argon isotope. We can do uranium track dating. Oops, I can't write with this mouse. Uranium track dating. This looks at the radioactive decay of uranium. But when uranium decays, because it's such an energetic element, it actually moves in the substance in which it's been trapped. And so we can measure the length of those tracks, and it gives us a fairly accurate account of how old or when that uranium was deposited there. And of course, we're looking at volcanic ash. So we're looking at the age at which the volcanic ash was deposited. So when it was still wet before it dried, because it's mixed with mud before it dried, when it was still depositing there. So uranium track dating. We can also use thermoluminescence. Thermoluminescence allows us to look at the age of glass particles. And because it's a volcanic eruption, there's silica that has been turned into glass. We can measure the age of those glass particles. And so we can get a very good idea, incredibly accurate idea, because we have 4 ways to corroborate of when these footprints were laid down. Because you have the volcanic ash, you have individuals walk across the volcanic ash, compressing the volcanic ash underneath their feet. And of course, more volcanic ash is falling down on top of it. So the volcanic ash in their footsteps, in the footprints they left, are denser because they've compressed it with their body weight than the volcanic ash that falls on top of it. And so now you have a difference in the density of the matrix. And so when this erodes away, what it leaves is this much more densely packed volcanic ash from where their footprints were. And so we can date date these. It dates to, I think, about 3.9 million years ago. And that lets us know the kind of general kind of hominin that we're looking for. We know it's a hominin, by the way, because we see convergent big toes. We haven't talked about any of these things yet, but the big toe is in line with the rest of the toes, instead of like an ape or another primate, where the toes are divergent, so they operate like thumbs. And so we can date these, and based on the date, we know that we're looking at Australopithecines, or Australopiths, either way. We're looking at Australopiths. And at that age, we have a good candidate. That'd be Australopithecus afarensis. That's, if you've heard of the famous fossil Lucy. Lucy belongs to Australopithecus afarensis. And so we can then compare the anatomy that we have here to Australopithecus afarensis's skeletal anatomy, which we have. We have lots of fossils of afarensis, and it's very likely that the species of hominin that left these footprints belong to Australopithecus afarensis. And so this is in Tanzania, by the way. I don't think I said that earlier. This is in Tanzania. It's about 3.9 million years old, and these are left hominin, most likely Australopithecus afarensis. So anyways, the whole point of this is, one, to let you practice using their terms, but mainly to give you a taste of what it's like to design a project, the kind of first steps that you take when you're starting to think about doing some kind of scientific research project. If you have any questions, please post them as a reply to this announcement, because I'm going to post this in an announcement, and I look forward to hearing from you.